Okay, so let's see. So let me just quickly go over what we are going to cover in the exam one or midterm one, and that is essentially kinematics, and that covers constant velocity or constant acceleration, and essentially just describing motion in terms of position, velocity, uh, time, all the tools that we have to describe this, that is graphs, motion maps, describing things in words, numerically or quantitative, quantitative mm, quantitative part. And then there is this part about momentum and its conservation. Momentum and conservation of and its conservation. And finally, there's also going to be a question on coding. And essentially, the only code that you really need to look in detail is the 1D simulation, that is moving the sphere in one dimension. The thing that was also due as an assignment. Okay, so these are the things that are due on my midterm. If people have things, if people have things that they want me to review and have questions about, so I guess the best way to do this is if you just list out everything over here, and then we'll go over them one by one. So I guess questions. So if people have things that they want me to review or just go have questions, just let me know now. If you don't want to talk into this conversation, you can always type into the chat and I can see it from there.
Can we go over coding 1D simulations?
Okay. What else?
Describing the relationships between the three graphs.
Anything else? Oh, sorry, I see another thing. Another question from Maggie.
Will we be covering 2D dimension at all on this exam?
So there will be conceptual 2D questions, but nothing numerical, nothing that requires you to sit down and calculate angles and things like that. So there'll only be conceptual questions on it. Okay, so you won't have to ever calculate a vector on the exam, if that is fine. Can we go over question 1B from the sample exam? So question 1B from sample exam. What else? Will the answers from in-class worksheets be posted online? Yes, they will be. So answers will be posted tonight. For the in-class worksheets. Do people have any other questions that they want to ask? Okay, so I mean, if you think of something later on, just type it in. And at any point, if you have questions, you can always type it in or just stop and ask me questions. So maybe I think the best way to go about this is to start from the beginning, which is this thing, right? So describing relations between graphs. We're not going to have, I'm not going to go over this. There's not much to discuss there. Then maybe we'll go over 1D from the sample exam, so that'll be a good example to work out, I guess. And then finally, maybe coding 1D simulations. Okay, more questions. So question 3 on the sample exam had some information about springs and forces. Are we expected to know that? No, you do not need to know how to do anything to do with springs and forces. That was just a sample exam from some previous year which had done that at a different time. So that's about it. No, the topics that are covered are listed here. So that there's no spring or forces or anything of that sort. Okay. Okay, the next question is, will we be expected to do anything similar to the challenge question on constant acceleration worksheet, or will it be most likely the first 6 questions? No, you will not be expected. So, okay. Yeah, I would say it's somewhere intermediate between challenge and the first 6 questions, and it's nothing like the super challenge question. Are there going to be any energy pie charts? No, we have covered energy pie charts in week 3. Week 3 material is not covered in this exam. So it's only week 0, 1, and 2. So whatever we've covered in these weeks is what's going to be on the exam. Okay. So everything that we did on week 1, so the ball bounce activity and onwards is not on the exam. So there's no energy and things like that. Okay. All right. So yeah, if people have questions, they can just keep typing, and if I don't look at the chat, then remind me that I'm not looking at the chat, and so I can then answer the questions. Okay. So maybe let's just go up and start from describing relations between graphs. So. To take it from the beginning, we have every time we're describing motion, we need to define a origin and reference frame. And once we have defined a origin and reference frame, then we can start describing the motion in terms of these 3 quantities, so position or displacement. Right, displacement is nothing but the change in position. Velocity, which is just the rate at which the position changes. And then there's acceleration. All of this, how these change with respect to time. And this is how we try to go about describing motion. And so there are various relations that one kind of has to that we figured out in class. And for example, we have let's see, where do I start from? So maybe let's start from something like this. Suppose I have a constant velocity graph. Right? Then I can always draw a position versus time graph that maybe looks like this, okay? Or it could possibly look like this also, or it could possibly look like this, right? And all 3 of these are correct as long as I have not specified the origin, because if I choose, this is really represents the freedom to choose origin. Now, unless otherwise specified, that unless someone is saying that, no, this has to be your origin, I'm forcing you to choose this to be your origin, then there's all these possibilities are correct of choice of origin. And so what is the relation between going from here to here? So let's see, from going from the position versus time, the velocity versus time is nothing but the slope of the graph, right? So the slope of the graph is nothing but given by rise over run. So for example, if this happened to be, let me just redraw this. So if this happened to be a position versus time graph that looked like this maybe, and so let's just take that point. So this is 2 seconds, this is 0, this is 2 meters maybe, and this is time here. Then rise over run is nothing but velocity, which is 2 minus 0 meters divided by 2 minus 0 seconds. So that's final velocity minus initial velocity, and this is final time minus initial time. So that's just rise over run, and so I get 1 meter per second as the velocity, right? So when I draw a velocity time graph, I immediately know that the corresponding velocity time graph should be 1 meter per second, and I would have a graph that looks like that. Okay. Now that's talking about going from from a position time graph to a velocity time graph. Suppose I wanted to go from a velocity time graph to a position time graph. Then this is just nothing but the reverse. So from calculus, if you remember, slope is nothing but the derivative. So the reverse is just the integration, which really means I need to find the area under this graph. So area with respect to this axis, right? So let's take an alternate example. So let me take this example of say negative velocity. And so if you remember from calculus that if you're calculating area under the graph with respect to the axis, that's what you need to calculate. So suppose this is 1 meter per second, and this is say 1, 2, 3, 4 seconds, right? The velocity time. Then the area under this graph is going to be 1 meter per second. So that's this length, right? So it's just area of this rectangle multiplied by 4 seconds, right? So that's so the position or the change in position. So really the displacement is this is minus 1 meter per second. So displacement is going to be minus 1 meter per second multiplied by 4 seconds. So that's just the area under the graph, and so that's minus 4 meters, right? So a position time graph would then look like something like this, where so I have after 4 seconds, I have traveled minus 4 meters in 4 minutes. Okay. So again, and you can go backwards and check that this makes sense. That is, if you take the rise over run of this, you find the slope of this graph of the velocity time graph, then I should get back minus 1 meter per second. And so that's a negative slope of that. Okay. So all of these are just calculus relations that we do. And so the same thing applies now when I go to acceleration now. So this is all just constant motion, but non-constant motion is just a generalization of this. So suppose I have a velocity time graph that now is not constant, but does something like this, for example. So maybe after 3 seconds, initially it starts off from 0, and maybe after 3 seconds, this has gone up to 3 meters per second. So that's the velocity after 3 seconds. And so then the acceleration time graph is, again, you repeat the same thing. It's rise over run. So the derivative of this velocity time is going to give me the rise of the slope, which is nothing but, in this case, again, 3 meters per second. So that's this length. The rise, and divided by the run, which is 3 seconds. So that's just going to give me 1 meter per second squared. Okay, so the acceleration now is just 1 meter per second squared, and so I can end up drawing a graph like this. Okay, so that's 1 meter per second squared. Okay, and so I can do the reverse as well. That is, if I wanted to find, if I was given an acceleration time graph and I wanted to find what the velocity time graph looks like, then again, it's just nothing but the area, right? So maybe after 3 seconds, I wanted to find what the velocity is. So then this length is 3 seconds. This length is 1 meter per second squared. So then after 3 seconds, I know that the velocity is 3 meters per second. Okay. For non-constant motion, we also want to then go and link velocity with position. So now if I want to go to a position time graph from here, again, it's just the same area under the graph, right? So maybe after 3 seconds, I want to calculate what the change in position is. Then this is nothing but the area under this graph. So which is, again, this length is 3 seconds. This length is 3 meters per second. So that's nothing but the area for a triangle. So that should be half times 3 times 3, right? So half multiplied by 3 multiplied by 3, which is nothing but 4.5 meters. Okay. So now at this point, I have to be a little careful because suppose I'm starting from the origin. I know that the final displacement is 4.5. So after, oh wait, this is supposed to be 3 seconds. So maybe I put it there. So 1, 2, 3, 4, 4.5. So 3 seconds, I have traveled 4.5 meters. So now the question is, which way does this thing curve, right? So just like in calculus, if this is constant, this goes as a linear shape. This is going to go like a quadratic or parabolic shape, right? So but there are many options. Which way does it curve? So if velocity is increasing with time, then initially it's starting off with 0 velocity. So it's going to be a small, a flattish graph, and then it has to start increasing its slope, right? So that's quadratic upwards that way. Okay, so it's not going to be something like that looks like this, for instance. Curving downward, you're not starting off with a large slope and then slowing down. So it cannot be this. So this is wrong. And this is right. Okay. So these are the ways you see these relations. And there's only a finite number of these relations like this. So for example, one thing that we did in class was we looked at this thing like, okay, suppose I have acceleration and velocity. If the velocity is positive or negative, and the acceleration can be positive or negative, then what does that actually mean for the motion of the graph? So that means if they're both positive, if both acceleration and velocity are positive, then it's speeding up. Similarly, if they're both negative, then it's still speeding up, right? And if they're opposite signs, then it's slowing down, okay? So then how do I actually draw graphs for this, for a situation like this? So for example, if I throw, let's look at the scenario where I've thrown a ball up, right? I throw a ball up after some time. So let me just draw a motion map for that. So I've thrown a ball up with the initial velocity. It's slowing down as it reaches its peak height, and it stops for an instant when it reached its peak height. Then it starts speeding upwards, right, and comes down. So in this scenario, I know that the acceleration is just going to be minus 9.8. So let's say an example of ball thrown upwards. So I know the acceleration is always just minus 9.8 meters per second, or just minus 10, let me say, roughly minus 10 meters per second square. By the way, in the exams, if you use minus 10 or minus 9.8, doesn't matter. Either way is fine for me. Yeah, so now then I know that this is a negative acceleration. So the velocity time graph has to have a negative slope, right? But where do I actually draw this line? Should I draw the line this way, or should I draw the line like that? How do I actually draw this line, right? So this is where the motion maps comes in handy, right? So you can actually see what's happening here. So you're starting off with, so if this is my positive y direction, then I am drawing, say, the positive y versus time. Then what is happening initially? It's initially moving with a positive large positive velocity. So I know I'm going to start off with that. And at some point, the velocity is 0. So I know I'm going to stop somewhere there. But eventually, it starts increasing in the negative direction and until I have a large negative velocity, right? So that is where the motion map is really useful. So you probably should draw it like that. And so then I know, sorry, this should not be position, but this should be velocity, sorry. Velocity versus time. And so this is a straight line pointing down, and then you can check the slope. Yes, this is a negative slope. So yes, this also makes sense with the acceleration versus time graph. Okay. And if I wanted to say calculate what the position versus time graph looks like, so then I know, for example, there are two regions over here. Region 1 is where the velocity is positive. So this is this region. And region 2 is where the velocity is negative, right? So if I have, so what acceleration is always negative, right? So I have a region where velocity is positive and acceleration is of the opposite sign, which means that this must be slowing down, right? So it starts off, again, the motion map again comes in handy here because I know it's starting off with a large initial changes in position. So when I draw the graph, it's going to look something like that, right? And eventually it comes to a stop. And so therefore it must reach a peak height, right? So it's curved this way. And then when both velocity and acceleration are the same sign, it's starting to speed up. So it then comes back down all the way. Okay. So this is the thinking that you should have when you're constructing this entire picture. And this is why motion maps are so useful also to help you visualize what's going on. And it's not enough to just stop at the graphs, but also then say in words, right? It's important to say in words what is going on, right? So for example, the ball started moving up with a constant velocity, but is slowing down until it reaches a stop at its peak height. And then it starts increasing in a negative direction. The velocity starts increasing in a negative direction until it comes back down all the way. Okay, so it's important to even say that in words other than visualizing everything with all these tools. Okay, and again, the only relations that really exist between these graphs are calculus relations, right? So if I want to find the height that the ball traveled, I understand that this point over here correlates with this point over here, right? Because this is where the velocity is 0. This is where the peak height is. This is the peak height. So if I wanted to calculate the peak height, again, it's nothing but the area under this graph, right? So it's just, suppose this was 10 meters per second, and this was well, it can't be anything else but 1 second, right? And the reason why this has to be 1 second is because if I calculate the rise over run here, then this is minus 10 meters per second squared, right? Which is what the acceleration graph should look like, right? So 10 meters per second, and this is 1 second. Then this is the area under this graph is nothing but half multiplied by 10 multiplied by 1, which is 5 meters. So this height is now 5 meters, right? So I can do all of this math without actually ever referring to any formulas. And it's important to do this without the formulas, so because then you won't make a mistake. If you use formulas, you will most likely make mistakes. Okay? The formulas are there just for you to cross-check to see if you really are stuck. Then go to the formulas, see what's going on. Okay. Okay, I think so. Does anyone have any particular questions about this relations between the different graphs?
How would you define a reference frame according to this example?
So sorry, can you say that again? How would I define a reference frame for
this example that we just did with a ball?
Okay, yeah. So again, if the reference frame is not given to you, you can choose it. So in this particular example, what have I done? I have chosen a reference frame, right? Which means that I have chosen a positive y direction to be upwards, right? And I've also chosen an origin from my position time graph, right? If I've chosen my origin to be, that is the origin is when I'm throwing the ball up, so it's starting from the initial point of release from my hand. I could have chosen a different origin, right? I could have chosen, for example, I said, no, I want the maximum height to be my origin. In which case, what would that graph look like? if the maximum height is at 0, then all I'm doing is just shifting the whole graph. I'm just shifting the coordinate axis. That's all I'm doing. I'm starting to measure from maximum height. So I could have shifted the origin. Alternatively, I could have also said that no, this is up is not my positive y direction. I could have chosen down to be my positive y direction, right? In which case, everything would flip. So now if down is positive y, then acceleration is downwards, which means acceleration is plus 10 meters per second square. The velocity also has to reflect that, which means that it's now it has a positive slope. And so initially when it's moving upwards, it has a negative velocity, right? So that's what a velocity versus time graph would look like. And then finally, a position versus time graph should also reflect that, meaning that I start off moving in the negative direction. Suppose, again, if I'm choosing the origin to be my hand, then I start off from the negative direction and then come back into my hand. So everything just got flipped. That's all I'm doing. But if I try to repeat all these calculations and try to find out what's the displacement, what's the position, again, just using areas of graphs or slopes of lines and things like that, they'll still give me consistent answers. They have to be consistent with each other, right? The thing that's if I choose a graph of acceleration versus time that looks like this, and then correlated with that, then this is wrong, okay? Because then I'm mixing up different reference frames. That is not allowed. Does that make it clear?
Yeah, so like when we're just defining the reference frame, we could just show on our graph the draw y with an arrow pointing upwards or downwards, showing it's positive or negative.
Yeah, so that's best done with a motion map. So for example, when I draw a motion map, I always draw my origin and reference frame. So I would draw the origin and I would draw the positive y direction to be that. Okay, so that way this completely defines everything. And so I know that the origin, that means the origin is over here, which is the starting point of motion. So that means my position time graph also has to have the same origin. Then I know what the positive directions are also, so then I know everything else. So that's best done with motion maps. So if you draw a motion map instead that look like this, so I said, let me just choose my origin to be here, and then draw the position time graph, then it would be for this particular choice of origin, this would not be the correct position time graph, right? Because here you're telling me, oh, that it's the ball's actually starting from some negative side and then crosses over to the positive side. Does that make sense?
Yeah, thank you. That makes way more sense now.
Okay. Any other particular questions about this relations of graphs and things like that? All right. If not, then let's move on to the next thing. So, which I think was, what was it? It was 1B from the sample exam. 1B. So let me actually pull that up. Um, 1B. Okay, so I actually don't remember what this question is. So let's see what all it says. It says, well, there's a lot of information here. So there's the fast herbivores, there's a cheetah and a Thompson's gazelle. The acceleration for 0 to 90 kilometers for Thompson gazelle is 18 seconds. Takes 18 seconds to do that. Max speed is 90 kilometers per hour. Cheetah, an acceleration is 0 to 120 kilometers per hour in 3 seconds. Can maintain a maximum speed of 120 kilometers per hour. but can only maintain it for about 30 seconds. Okay. Consider a very simple model of a predator interaction. Assume the cheetah creeps up on a resting gazelle, ending up a distance d away. At the moment t equal to 0, the gazelle sees the cheetah and both take off in the same direction, accelerating as fast as they can. The cheetah catches the gazelle during the period when they are both accelerating. Okay. So draw, maybe let's just start with the first part, which is draw qualitatively correct, showing relative slopes of position time, velocity time, and acceleration time graph, and motion maps. Okay, so let's see. Let me just write all that information down here. So there's the cheetah, and there's the gazelle. So the information about the cheetah is that its max speed is 120 kilometers per hour. For the gazelle, it is 90 kilometers per hour. The acceleration is 120 kilometers per hour in 3 seconds. So that's 120 kilometers per hour divided by a unit conversion. So I have to convert all of these units. So let me actually just do that here. Yeah, so that is 33.3 meters per second. In case you're wondering how to do this unit conversion, it's essentially a kilometer is 1,000 meters, right? An hour has 3,600 seconds. And so this is nothing but, if I try to change this thing, sorry, if I simplify this a bit, it just looks like 5 by 18 meters per second. So I multiply 120 with 5 by 18, and I will get 33.3333. Then, the Thompson's Gazelle has, it accelerates from 90 kilometers per hour in 18 seconds. So that is 25 meters per second. Oops, I made 33.3 meters per second divided by 3 seconds, which is 11.11 meters per second. This is 90 kilometers per hour, which is 25 meters per second divided by 18 seconds, which is 5 meters per, sorry, this is meters per second square. This is 5 meters per second square. Okay, so I have all of this information. So what's happening? There's this cheetah over here. So let's see, that is my drawing of a cheetah. And there's a gazelle. And they are a distance d apart. And what else am I told? They both start moving with the same acceleration, right? So let's start with the thing that I like the best, which is the motion map itself. So so let's choose the origin to be with the cheetah. Okay, so if I choose that to be the origin and this to be the positive direction, and they both start accelerating in this direction. So then for the motion map for the cheetah would look like, so for the cheetah would look something like this. So I start off, I'm starting to increase my speed, or the cheetah is starting to increase its speed, right? Okay, and for the gazelle, maybe let me use a different color for that. So the gazelle, I have again, the origin has to be the same because I'm drawing it comparatively. It doesn't make sense to be using two different reference frame when I'm doing for two different objects when I'm trying to compare their motion. So the reference frame is the same, and so but this time the gazelle is starting some distance d away. Right, so it's starting from some distance d away. It also starts accelerating, but its acceleration is slower. Right, so the arrow lengths increase at a slower rate. Okay, so that's what the motion maps look like. Okay, so from this now it's easy to then translate to all the other graphs, right? Which is what should the position versus time graph look like? The cheetah. So let me draw that in green. So position versus time graphs. The cheetah is starting from the origin and is accelerating in the positive direction, right? And so suppose, so it's increasing its speed, and so I know that this has to be curved upwards like that, where the slope of the curve keeps increasing. On the other hand, I know that the gazelle is starting at time t equal to 0 at some distance d away, and eventually the cheetah does catch the gazelle and is accelerating slowly, so it's not going to be as sharply curved as the cheetah's curve, but it's going to be a slower curve, right? And eventually the gazelle catches the cheetah, right? So let me just mark this as gazelle, and so this one is the cheetah. Okay. So now you can also look at what the velocity versus time graphs look like, and you can infer that from the motion maps and the position time graph. So the cheetah at time t0 has a sharper change in velocity, right? And in fact, we know what that slope should look like, right? Because that's just given by the acceleration. So let me just use cheetah. Oh, I mixed up the colors, but that's okay. So this is the cheetah, and the gazelle also starts from 0 velocity, right? You can see that from the motion map, but is now just moving at its velocity changes at a slower rate. Okay, so that's gazelle, and similarly for the acceleration time graphs. So this one's velocity. For the acceleration time graph, what I have is that it's again all positive. So the cheetah has a higher acceleration, and the gazelle has a lower acceleration. So acceleration over here for the gazelle, which we've calculated up here to be 5 meters per second squared. And for the cheetah, which we calculated to be 11.1 meters per second squared. Okay. All right, so that's question 1A. Let's go see what question 1B is asking. Wait, let me just wait. Velocity time, acceleration time, and motion maps that would represent both. Okay. Find the final position when the cheetah would catch the gazelle and the maximum velocity that each of the animals reach. Okay, so so over here you are actually, so there is something slightly open-ended about this. Okay, which is you're not given the initial distance d away. Okay, so but what you are told is you are told that the cheetah catches the gazelle during the period when they are both accelerating. Okay, so that means then neither of them has reached that maximum speed; they're both accelerating. Okay, so one could so in principle, this distance can be a really small number, but it can't be a large number. Okay, so you can't have d to be a large number. So what's not given to you is d. So this is the slightly open-endedness about this. But what I can calculate is what is the maximum value that d can be. Okay, so the maximum value that D can be is, in fact, that the cheetah accelerates for 3 seconds, right? So, which means that, sorry, where am I? Yeah, so sorry, the cheetah accelerates for 3 seconds, accelerates for 3 seconds. So suppose it needed to accelerate for 3 seconds to catch the gazelle, that means that would have been the maximum value D should have been, okay? If it only needed to accelerate, say 2 or 2.5 seconds, then D would be smaller. Okay, so there's not enough information given to you over here to solve the exact number of D, but you can solve for the maximum value of D. Okay, so the assumption that you have to make is that the cheetah catches gazelle after 3 seconds, and this corresponds to the maximum distance, right? You cannot choose more than 3 seconds because beyond that the cheetah cannot accelerate, and so at least according to the description of the problem, it says that the cheetah catches the gazelle during the period when both of them are accelerating. Okay, so let's actually try to calculate that. So so if it has if the cheetah catches the gazelle after 3 seconds, then we also know what that velocity should be, right? We've calculated it up here. That should be 33.33 meters per second. Now, at this point, you are free to use kinematic equations, or I will just use the graph over here because I know what that is. So it's 33.33 seconds after 3 seconds, right? And so the cheetah travels a total distance of, again, this length is 33.33. This length is 3 seconds, right? So that means this is nothing but the area under this graph, the area of the triangle, right? So let me just shade that a bit. The area of this triangle is going to be half times half multiplied by 3 multiplied by 33.33, which is about 99.99, which, sorry, 49.98, so which is about 50 meters per second. So it's approximately equal to 50 meters. Okay, so and I know that the maximum, the position of the cheetah is 50 meters. So that means that's this. Okay, so I can then state. I mean, the question only asks me what the the question is asking me if I calculate the final position of the cheetah. So I've calculated that. But now the question is also asking me what is the final velocities of each animal. So I can also calculate that from this graph here. So the gazelle is traveling at 5 meters per second square in 3 seconds. So in 3 seconds, it would have reached a speed of 15 meters per second. Okay, so that's how I would go about answering this. Now, in principle, one can also ask more questions about this. One can ask questions about like what is the maximum value that D can be, which is not asked in this particular sample exam, but one can also go about trying to calculate that as well. Yeah, hopefully this makes it clear. Do people have any questions about this? Okay, so I don't see anyone saying anything. So let's then move on to the final thing, the coding with 1D simulation. So I think the best thing for me to do is actually just to tell you about like what's the best way to prepare. And I think I sent out there's a video link I sent out to everyone, which is essentially one of your ULAs, Anuj, who's made a video describing each and every step of what's going on in the program. And that's a nice way to prepare also for this, to understand what's going on in each and every line of the code. On the exam, you will be given the whole code. You won't have to memorize that code. Okay? So you don't have to memorize any code or anything like that. You will be interpreting each line. You will be checking, answering questions about what happens if you change a particular line to something else. Those are the kind of questions that you will be asked on the exam. Okay? Let me just try to pick up the code itself. Yeah, and I think even in the there's a example questions and solutions also on the exam folder in D2L, which has what kind of questions you'll be asked. So in that you're given the whole code, exactly the same code that you worked on within class, and so you can just use that as a you can just follow, like, try to answer the questions over there. So let's see. As I told you before, the important thing about coding is that the first part of a code is all about defining objects. And the second part of the code is about manipulating those objects. Okay. Usually these are done in loops, so you go over them iteratively. And at least the loop, the only kind of loop that we have dealt with so far is called a while loop. So if you look at the code, it says there's a line which says something like while t is less than tf, then do the following steps. Okay, and inside this following steps, it updates the position each time. The position, what is it called? Sorry, particle.pos. Is equal to particle.pos plus particle.velocity star delta t. Star means multiplying, so star delta t. So all it's doing is that it takes the position at some time. Suppose the position was 1 meter, then it takes the velocity. So in fact, sorry, let me actually write it properly in the Python notation, which is particle position. I think you start off with something like 0, 1, 0. So this is the x component of position. This is the y component, and that's the z component of position. And the velocity is defined in some line earlier on as a vector again of 1, 0, 0. Right? And so what we're doing here again is defining the x component of the particle velocity, the y component, and the z component. So we're only really interested in 1D motion. So that's why the velocities for the y and z are set to 0. And so effectively you can just ignore them, right? If you wanted to simulate 2D motion, then you would have to include some velocities for the y and z components, 2 or 3D higher dimension motion. So initially the x component is 0. Then I update that with particle velocity. So the x component, I'm only writing the x components now. So that's 1 meter per second, say, multiplied by delta t, which is defined to be 1, right? So then this just becomes 1, right? Then it goes back into the loop. At the end of the loop, you'll see there's a t equal to t plus delta t. So now initially t started off to be 0, delta t is 1, so then t is also updated by 1. So then once this happens, it goes back into the while loop and checks, is t less than tf? And tf was defined to be 10. So it checks it checks whether this condition is true. It checks, is 1 less than 10? Yes, that's true. Okay, that means let's do this again. Okay, and in this case, in the next iteration, what happens is that the new particle position is now 1. Okay, and this thing is still the same. So that means you're adding 1 to 1. So this becomes now 2. Okay, it goes in here into the last step of t equal to t plus delta t. So that means now t is 1 plus delta t is 1. So this becomes now 2, right? It goes back up here and checks, is 2 less than 10? And then it says, yes, it is. So therefore, let's continue doing this again. And this keeps happening until at some point you reach, say, t equal to 9, right? And so 9 plus 1 will give me 10, right? And then when it goes back up here again to the top and checks, is 10 less than 10? No, technically it's not, because 10 is equal to 10, so it'll stop doing anything, right? So at that point of the code, your ball stops moving. Okay. So that's all that's happening in this code. You're just updating the position each time by multiplying particle dot velocity with delta t. Okay. Does that make it clear? Do you need a little more explanation on that, or anything particular that's still confusing? Oh, sorry, there's a question.
On the exam,
Yeah.
we will be only given a while loop.
You will be given exactly the same code that you were given on. In fact, you know what? You'll be given exactly the same code that's there on the more examples with solutions under the exams folder on D2L. So this is exactly the same code that you had on the 1D simulation problem. You'll be working with exactly that thing.
Okay, and we're allowed to use our equation sheet as a cheat sheet, right, for the exam?
Yes. So you use the equation sheet. You can write. So that should just be printed on one sheet of paper, right?
Okay.
One US letter size sheet of paper, and you can write anything on both sides of the paper, and write whatever you like. Some suggestions are, if you can't remember how the graphs should go, what if something is speeding up or slowing down, put them in. If you're having trouble remembering what certain lines of codes are doing, put that in. The formulas are there already, but I would advise you to make small notes on those formulas, saying what does that actually mean, how do I actually use it, right? And what also might help would be things like a particular example that you worked out that might just be useful also, that to help you remember, oh, this is my strategy to deal with these problems.
Someone asked a question, does the cheat sheet have to be typed or can it be handwritten?
No, so the formula sheet is available on D2L, right? So you print that out and then you write out whatever you need on the formula sheet. Does that make sense? I mean, if you want, you can type over it on a PDF, but that seems like too much work. Does that make sense?
Yeah. There was another question saying, what was the max velocity for the Gazelle for the previous example?
What was the max velocity? So I think we went over that. Oh yeah, I think I just said it in words. But so we know that we're calculating this particular scenario. So we're after making this assumption. Oops. After making this assumption that we're going to deal with the acceleration for the entire period of time of 3 seconds, then I can make this. I can actually calculate what that velocity is, because I know the acceleration for the. Oops. Sorry. Okay. So I know the I know the time that the Gazelle traveled. I know that I know what the acceleration for the Gazelle is. So again, if I try to figure this out from area under the graph, the change in velocity after 3 seconds is nothing but 3, right? The area of this graph is 3 multiplied by 5. So that means this should be 15 meters per second. So after 3 seconds, the Gazelle reaches a speed of 15 meters per second. All right. Are there any final questions people have?
Can you explain how the lab group activity is going to work on Tuesday?
Yeah, so I think that's also there on the slides. Essentially, all that's going to happen is you're going to use an IOLab. You will be given some graphs to reproduce with the IOLab. And you will be asked questions about those graphs, and maybe compare. You'll be asked to maybe draw idealized versions of them and compare what's going on. You will be asked to upload those graphs that you got on IOLab into D2L, and you'll also have these handouts, which each group submits just one of those handouts back, and that's about it. Does that make sense?
Yeah, thank you.
All right, so I don't see any more questions coming from anyone. So I will end this meeting. I will post this video and a link to the video on D2L if you want to go over it. Best of luck for your exams, and have fun preparing.
Thank you.
Yeah, you're welcome.
Thanks.